Okay, sorry. My camera has been hasn't having some issues. I had to sort that out first. As I was saying before, in order for us to define a plane, we need two things. We need a normal vector to the plane and some given location or some position. The thing is, if the position has, well, you'll be given an already known position x naught in 3 space, and for you to fully describe a plane, you'll be given some abstract points that you don't know, and that would be a position vector from that point that you don't know to this given point. So it's going to be, since it's a position vector, it's going to be, and this is already a known location in space, and you want to make a position vector from a different location in space that you don't know what the point is at that time in space, at that point in space. So the position vector is going to be x minus x naught, y minus y naught, z minus z 0. These are vectors. Basically, there's two ways of writing a vector. In either the standard basis vectors or using brackets. I don't know what this one is called. So you can write it as x minus x naught I plus y minus y naught j plus, these are standard basis vectors. We'll talk about that when I'm doing my video series from tomorrow. I just want to, this is not part of my video series, I just felt like doing this. Plus k. Yeah. These are standard basis vectors. Okay, we don't actually need this. So this is a position vector. And a normal vector, because you need two things, which is a given location and a normal vector. A normal vector is a vector that's orthogonal to the plane or perpendicular to the plane. So you have a normal vector given y. What are we looking at? Oh, how am I writing arrows? AI. Don't fall down. Yeah. So this is a normal vector. So for you to geometrically understand this, no. So normal to the plane. So this is at 90 degrees to the plane. So this is like some closed plane. It's not opened. Okay. So if we did a dot product between this normal vector and the position vector, we get 0. Therefore, they're orthogonal, right? So a x minus x naught plus b. I think I have to arrive this in the last video. I think I did, but I'm just gonna, yeah, I did. I'm just gonna run over it then. I did this in the last video, so I was gonna run over it. Wait, but we know something there. What do we know? We know that the normal vector is given by the gradient. Okay? This is true a normal vector to a plane. Also, this is also given as the normal. And we know what this is. Therefore, we can say that the normal is equal to partial of w with respect to x first, plus the partial of w with respect to y, plus the partial of w with respect to z. So we have this as, this is the normal vector. If we use something called the idempotent rule, the rule of idempotency, you see you can map all components to themselves. Map this to this, map this to this, and map this to this. So we can say that the equation of a plane, oh, we're gonna write this, I don't want to bend down, plane is given by partial of w with respect to x times x. I'm going to explain some sort of ambiguity in this thing there. Plus partial of w with respect to y, plus partial of w with respect to z equal to d. What is the ambiguity? What makes it, it's not difficult to grasp, it's just, it doesn't seem like it, yeah? Why doesn't it seem like it? Because, I guess I have to answer my questions now. Because this is a number. This is not a number. This is a scalar factor. A scalar factor is a sort of an equation or formula where you have functions of the independent variable, yeah? Without any direction like I, j, k, I prime, or whatever. So this is a number, and this is a scalar function, or scalar factor, sorry. Scalar factor. Scalar function, scalar factor, nah, sort of the same thing. The difference is, they're actually the same thing. The difference is, this is already a calculated number, this is not calculated. So you get this number from doing this. So let's say the point, let's say you're asked to find the tangent plane. So, okay, let me summarize everything. This is the equation of a tangent plane. We use the normal vector, in quotes, the normal vector to define the tangent plane. We can also talk about the tangent line as well, but let me just explain this first. So we use the normal vector because the normal is orthogonal to the tangent. I told you what a tangent is. The tangent is the first derivative of the vector function. If we know the slope of the normal vector, well, in 3D you lose that idea of slopes. You have vectors now. But anyways, so in order for you to get this number, you solve for this scalar factor. You have functions of x here, functions of y here. This is not part of what you're solving for. And functions of z here. So you have scalar factors where they are like functions. So if you're asked to find the equation of a plane at some particular point, let's say 1, 3, 2. So you put in x equal 1 here, y equal 3 here, and y equal to 2 here. So it's the same thing, it's just this is explicitly written or something. This is like a more broader form of writing an equation of a plane, of a tangent plane actually. A tangent plane to a specific point on some surface in R3 in 3 dimensions. So I think that does it for us actually. We know, okay, there's really nothing else we can do. We know how to define lines. I'm gonna go over these topics in my video series. This is not part of my video series. From tomorrow, I'll start from trigonometry. And the thing is, while doing all these topics in math, because I want to do it alongside physics. But the thing is, I can't do a different physics scheme because it's really wide. Physics is, to me, if you ask me, I think physics is, why didn't know mathematics? I mean, what mathematics is abstract. They're both abstract. But if you want to explain something in physics, you need to understand the depth of the mathematical concepts behind them. You need to understand them well. So while talking about some certain things in trigonometry, I can tip in some things like projectile motion, derive some equations for projectile motion. And then I moved to coordinate geometry. Coordinate geometry leads to vectors a little bit, but I wouldn't be moving to vectors after talking about coordinate geometry. So after coordinate geometry, I'll talk about because my coordinate, the way I'll do coordinate geometry, I'll do coordinate geometry in 2 dimensions and 3 dimensions. You see the difference. Well, they're not different that much, but you see the similarities between both of them. And then I'll talk about some things in 3 dimensions that I will not talk about till like later on. Then I move to complex number binomial series. And in my binomial series, I'm not talking about y plus x raised to the power 2. That's nothing. When you talk about binomial series, because in binomial series, you have to build it up from power series to Taylor-Maclaurin series, and then you use Taylor-Maclaurin series to derive the binomial series. And then in binomial series, you see how I will derive wouldn't derive it, but like I will explain something called the gamma factor. The gamma factor is something we use in relativity to explain how things happen in relativistic cases. I mean, that's not a good explanation, but when I get there, I'll talk about it. Like the gamma factor is given by 1 divided by square root of 1 minus v squared divided by c squared. You can actually write this as a binomial series, but I think it's going to be a divergent binomial series. I think it's convergent actually. Anyway, we'll talk about it. Because power is negative half here. It's the same thing as saying, because the binomial series is like 1 plus x to the power k, and this can be written as a function of, let's call this whole thing phi. 1 minus phi to the negative 1/2. So it's something like that, because the binomial series is like a function of x equal to 1 plus x to the power k. And we use k to know whether the function is divergent or convergent. So this is everything I want to do. So I'll start doing these topics, and then I'll chip in physics when I'm talking about Riemann's sum, and improper integrals I'll do some electricity with it as well. So like electric potential, because in electric potential you're using proper integral, you're integrating over an infinite region. So you have to be doing an improper integral due to infinite infinite interval. So it's not, there's some times where you have infinite discontinuity and so on and so forth. But we'll talk about that. So I'll really want to try to go deep, and everything I'm going to be doing, I'm going to do the proofs of all of them. So I didn't just want to give you an equation like these ones. I just gave you equations for it. But you see where we're doing vectors. I'll do vectors in 2 and 3 dimensions, because I believe that most of my subscribers are mature students. So I'll do everything in 2 and 3 dimensions. And you see how parametric equations actually relate to vectors, because parametric equations are vectors actually. So yeah, and then that's everything about it. So thank you for watching. Like, subscribe, leave a comment below. If you want to add, I would really appreciate if you guys can tell me what you want to add and what you don't like about the video. And also, if you like anything about it, tell me. I really want to do this. I want to go deep into, and then after I finish my scheme, actually, I'll go further and further to I might even do differential equations with that. I want to go further and further and further, and teach as far as I can. Thank you very much for watching. Have a lovely day or night. Bye.